This is A0 plus sum of theta 8i, right? And so, yeah, so the question is, so why is phi inverse an algebra homomorphism? Okay. Phi inverse takes A0 to this.
I want one time.
Yeah, so that's the question, right? Why is phi inverse an algebra homomorphism? And so it's because you write this as A0 plus, then these are the terms with theta in it. Now, if you have A0, B0, then that goes to A0 plus this. Just a minute. So, like, if you take this and this.
Yeah, how to?
And you multiply out, you get A0, B0 plus.
So just directly check by this definition.
Yeah. So these are the terms with theta in it.
I can by this one I can directly check how do you so just by this or you have some viewpoint to quickly see this is algebra homomorphism.
Well, this is how I see it very quickly. That it's an algebra homomorphism. Because
you can prove horizontal form solidify also horizontal form. So and it's a bijection, so you only need to check the constant term.
What it means that you see.
yeah.
So we apply it by phi. Yeah. And that's it.
That's right. Yeah. So this. Yeah, this is this, right? And so when you apply phi to it, you just pick out the constant terms. So you just get this. Yeah. So that proves that phi is an algebra homomorphism. Yeah, but it doesn't matter. If one,
But it's a bijection.
yeah, it's a bijection. So if,
you can also
yeah.
那你要确认就只是右边那一头还是后头，然后你就可以说你可以摆对。
所以等于我假设我一知道一开始就是homomorphism，那我造出了 inverse map， 我就可以直接说 inverse 一定是 homomorphism。用这个方法，它才是 left invariant 跟 right invariant， 这样应该就可以说它的 inverse 一定是。
条件有点。条件不是很好，就是这个条件太特别。
对啊，因为你现在是在所有的。
Well, actually, I think you just have to look at phi, right? So phi of AB, that is phi of A0, B0 plus the stuff with thetas. And so phi just takes the term without theta, and that's phi of A, phi of B.
我觉得你要确认就是这一项口中，除非你可以带5回来。 就是这个。
当然是好人
这当然是好人中，因为摆
对啊，
在
那你就可以直接代牌做这个。
可是你要证明这一项会真的等于phi inverse AB 的话，你要这个是 injective 吧？
对啊，那bijective。
Wait, no. I don't think you need that.
就是至少在 set 上，或者
到有正满吗？
有，因为你就是乘那个，你可以把这个分位再送来，是一样的。
Yeah. No, I think this is all you need to do.
你要验的是两边合成是一样的。
Yeah.
就两边合成是那边来的。
All right. Anybody else wants to hand in homework? Yeah.
爱不是我
因为右边的然后左边口
Huh? Yeah. You're not quite done yet?
Yeah.
Okay, that's okay. Give it to me this afternoon. Yeah, I think this will show that it's an algebra homomorphism. Right? Mm-hmm. Now, if A is horizontal and B horizontal, then AB is horizontal because the contraction and because the contraction is an antiderivation. So you apply the contraction to the product and it will be 0. So phi of AB is phi of, you multiply out, you take the constant term, and that's just phi of A, phi of B. Okay? So that shows the phi is an algebra homomorphism. I actually don't need to do this, because if phi is an algebra homomorphism and it's a bijection, then the inverse is also an algebra homomorphism. Okay. Now, Now the differential here, okay, we'll call the Weil differential, dW, and you have that because you have a D on the Weil algebra and you have a D on the round complex. So there's a D on the tensor product. Okay? And then you have this isomorphism phi. So if you start with an element in the Cartan model, you can go back to the Weil model, you compute its Weil differential, then you come back here to the Cartan model, and that will give you the formula for the Cartan differential, D. Okay? And I was going to do it, but it's a very straightforward technical exercise, and you get the formula. Okay? But I think instead of doing that, I'm going to talk about the applications of equivariant cohomology, so that you have some idea of what it's good for. And in any case, you can work out the formula for the Cartan differential yourself. And then you can look at the book. It's all worked out there also. Okay? So, today let's talk about now applications of equivariant cohomology. Okay. So, first of all, I should say that you can generalize all the theorems that we have done for a circle action to a torus action. Okay. Now, the equivariant Durham theorem is for any compact connected V group. Okay? But the localization theorems are for torus action. So, for example, so we have we will have a localization theorem for a torus action. Okay. It's not well. Okay. If it's not a torus, so if it's a non-abelian group, there's also a localization theorem, but it doesn't look like what I'm going to write down. It's a little bit more complicated. Now, if it's a non-compact, that's for a compact abelian group. Okay. A compact abelian group. No. What I mean is that if it's not abelian, if it's a compact connected abelian group, it's a torus. And so it will be the theorem of Atiyah-Bott and Berlin-Werner. Now, if it's a compact non-abelian group, then there's a theorem called non-abelian localization due to Lisa Jeffrey and Francis Kerwin. Okay? And it's a little bit more complicated. Now, if it's a non-compact group, then so far nothing is known. Okay, so that would be a research area, equivariant cohomology for a non-compact group. But for a non-compact group, it involves representations of non-compact groups. So that's very different from representations of compact groups. And it involves a lot of analysis. Okay? Yeah. For compact groups, it's more topology and algebra. But for non-compact groups, it becomes analysis. Okay. So this, for a torus, this is the theorem of Atiyah-Bott and Berlin-Werner. Okay. So it says, suppose a torus T of dimension L acts smoothly on a manifold M with fixed point set F. Now, the fixed point set does not have to be isolated. Okay? And it does not have to be zero-dimensional either. But we know that a fixed point set is always a smooth manifold. Right? We proved that. So if phi is equivariantly closed on M, any degree, it can have any degree, and you can still integrate on M, because phi, you can write it as a polynomial in U with coefficients in M, and the whole thing has to be invariant by G, not just the form part. Okay? But when you integrate, the U part don't do anything. You just integrate the form. And so it can have any degree because there's going to be some coefficient that has the right degree, right? And you integrate that. And all the others will give you 0. Okay? So you can integrate a form of any degree on M. And the theorem says that that integral is equal to an integral on t. Okay, you restrict phi to t. Okay, so I is the inclusion. Then this is a form, an equivariant form on t, but you have to divide by the equivariant Euler class of the normal bundle of F. So where I is the inclusion over F. That's right. I turned the integral into an integral on the fixed point set. Yeah. So I is the inclusion. Nu is the normal bundle of F in N. And E of t is the equivariant Euler class. Right? So of course you have to define all of those things. Now you are dividing by the Euler class. The Euler class, it's going to be a class. The Euler class is going to be a cohomology class in the equivariant cohomology of F. But it's going to be the top class. So F has dimension. We don't know the dimension of F. The top class. Okay. But F is a manifold, and M. Okay, M has to be compact oriented. Yeah. Now F is a closed submanifold of M. Therefore, F is also compact. And you can give it an orientation. It's got two orientations. But this is going to be, the top. In the top dimension, it will just be a polynomial ring. So here you're dividing by a polynomial. Okay, and so this is in the localization. Right. You are localizing by inverting all the polynomials in U. Okay. So this computation is done in the localization. But when you do integration, the U doesn't matter. Yeah. So what kind of answer do you get here after you've done your integration? I mean, what is the answer? Is it a number? Or is it a polynomial in the U's? Or is it something else? What do you think? I mean, phi is a polynomial in the U's. Okay? For a torus, you have L variables. So phi is a polynomial in the U's with coefficients in the forms. And then you divide by another polynomial in the U's, and then you integrate So what kind of answer do you get? I mean, this is actually going to be a rational expression in the U's with coefficients that are forms, right? Now, if you integrate the forms. And most of the forms will give you 0 because it doesn't have the right dimension. And there is just one term, with the right degree. And that will give you a number. So this should be a rational function in the U's, right? When you integrate a rational function in the U's with coefficients in the forms, you'll get a rational function in the U's. Okay? So, however, this part here this is a polynomial in the U's. When you integrate, you'll get a polynomial in the U's. Okay? So a priori, the right-hand side is a rational function in U1 to UL. Okay? But because the left-hand side is a polynomial in U1 to UL, the theorem says that rational function, it has to simplify to a polynomial. Okay? It's not necessarily a number because when you integrate this phi, maybe the top form does not have the right degree, so the top form will give you 0, but maybe it's some form in the middle that has some u's in it that has the right degree, and that form, when you integrate it, gives you a number, but you'll still have the u's. Okay. Okay. So this theorem is a simplification of sorts because here it's an integral over a fairly big manifold M, and then here this is an integral over a smaller manifold F. Okay, so it should be simpler. If the smaller manifold F is just a finite set, then you get a sum. Okay. Now, in evaluating that sum, right, you have to know what the function f is at the fixed points. So in problem set 4, I ask you to compute on CP2, and you don't need to know what the function f is, because all you need to know is the values of that function at the fixed points, right? You don't really need to know what that function is. And so in the handout that I sent you, I gave you a method for finding out, what the value of f is at the fixed points without actually finding the f. Right? Mm-hmm. Okay, so now let's write down a few applications. Now, the first application is to compute the integral of invariant forms. So we've done an example like that. So like the volume form on S2 is an invariant form. And you can find its equivariant closed extension, equivariantly closed extension. And then you can use the localization theorem. So, for example, when we apply it to the volume form, we found that the answer was 4 pi, right? So if you have an invariant form under a torus action, and the torus action has finitely many fixed points, and you can figure out what the f is at the fixed point, then you can calculate the integral using the localization formula, okay? And then the second application is to the computation of topological invariants. So topological invariants are numbers like the Euler characteristic, the Pontryagin numbers, or the Chern numbers. Okay. And here, so let me do an example. Now, many interesting spaces in geometry are homogeneous spaces. So homogeneous spaces are the quotient of a V group by a closed subgroup. So suppose G is a compact V group, and T is a maximal torus in G. So that's a torus of the highest dimension. So for example, say G is the unitary group, then the maximal torus is this subgroup. It's the diagonal unitary matrices. Okay? It's a torus because U1 is a circle. Then G mod T, it's the complete flag manifolds. The complete flag manifold of Cn. So what that means is that a flag is a sequence of subspaces. So it's 0 is in lambda 1, is in lambda 2, is in Cn. Lambda n is Cn, where lambda I is just some I-dimensional linear subspace. Okay, so a flag. This is a flag. So you have you start with a point, and then it contains in a line, and the line is contained in a plane. So that's a flag. 0 is in lambda 1, is in lambda 2. Okay? So that's an example of a flag. So if you look at all the flags in Cn, that's the complete flag manifold of Cn, and that is equal to Un over its maximal torus. Okay? And it's a complex manifold. So it has Chern numbers. So Un over U1 has Chern numbers. So Chen numbers, they generalize the Euler characteristic. They are topological invariants. And on the homogeneous space, you have an action of the torus T. T acts on G mod T by T applied to GT is TG T. Okay? So that's an action of the torus on the homogeneous space. And let's compute the fixed points. So GT is a fixed point of the action if and only if TGT is equal to GT for all T in T. Okay? And then that is G inverse TGT is T for all T in T. And so this says that G inverse TG, this times the identity is in here, so this is in T. Okay? For all little t in T. And so G inverse times the torus times G has to be contained in T. But G inverse TG, that's a diffeomorphism, so it preserves the dimension. So here you have a torus contained in another torus, but they have the same dimension, so they are equal. Yeah. So GT is a fixed point if and only if G inverse TG is T. What do you call an element G that does this? It's in the normalizer of T. Okay? So if and only if G is in the normalizer of T in G. And therefore, GT is in the normalizer of G in T divided by T. Now, this is a group. The normalizer of T in G is a group, and then this is a quotient group. Do you know what this group is called? Like if you have studied Lie groups, you have seen this. It's called the Weyl group. Okay, so this is the Weyl group of T in G. Okay? And what do you know about the Weyl group? G is a compact Lie group, T is a maximal torus. Then you have the Weyl group. And what kind of group is it? Like, if you have studied Lie groups, then you know that it's a very special kind of group. Yeah. What can you say about the Weyl group?
Finite.
It's finite. Yeah. It is a finite reflection group. That means it's finite and it has a set of generators that are just reflections. So the square is the identity. So the Weyl group so WT of G is a finite reflection group. Okay? So that means the fixed points are isolated. And now if you want to compute the Chen numbers of G mod T, you integrate. Okay, so it's the integral of Chern classes so it's the integral of the Chern classes of the tangent bundle of G over T. And then you get a Chern number if somehow when you multiply these Chern classes together, you get the dimension of the manifold. Okay, so then you have a Chern number. And you can use the localization formula to compute this integral, okay? Because in general, whenever you have characteristic classes, they always have equivariant extensions. The tangent bundle, if there's an action on the manifold, the tangent bundle has an action, so it's an equivariant vector bundle, and they have equivariant characteristic classes, and those are going to be equivariantly closed forms, okay, that extend this. So you can always apply the localization formula. And then, in this case, then you'll get a sum over the fixed points, which are the elements of the Weil group. And so you get a formula like that. Yeah, you see? Yeah. So the localization formula will give you formula for these topological invariants in terms of a sum over the Weil group. Okay? Now, so this can be generalized to a closed subgroup H of G. It doesn't have to be a maximal torus. It can be any closed subgroup, a maximal rank. So then, in that case, you get, say, the projective space. The projective space is un over u1 plus un minus 1. Okay? Or you can get the Grassmannian, which is un over uk cross un minus k. And so you can use the localization formula to calculate, the Chern numbers of the projective space or the Grassmannian. Yeah. Now I actually worked it out for the Grassmannian, so I'm going to write down the formula for the Chern numbers of the Grassmannian that I found. For example, so on the Grassmannian, you have universal subbundles, and they have Chern classes. So you can take the Chern classes of the subbundles, multiply them together until you get the right dimension, which is k times n minus k, and you integrate, then you should get a number, okay? So that number will be this particular Chern number. And the formula I found is that, okay, so I get a sum over the Weil group. The Weil group of the Grassmannian, it turns out to be permutations. And so you can you can index a permutation by a set of numbers, right? I1 to IK. And so you get a sum over these multiple indices. And then on the numerator, I have the product of R from 1 to K of sigma R UI1 UIK to the NR divided by the product over I in I and J in J of UI minus UJ, okay, where J is the complement of I in 1 to n. So I is a set of k numbers from 1 to n, and j is the other numbers. And so that's the formula that the localization formula gives you. As you can see, this is a rational expression in the U's. But it actually should be an integer, because these are integral cohomology classes. When you integrate, you should get an integer. Okay, and if you apply the localization formula, you will get something like this. You'll get a big rational number. Okay, but then you can use Mathematica to simplify this, and you'll find that it's an integer. Okay? And so the localization formula, it gives you all kinds of interesting identities. Okay? Yeah. Oh, yeah. And sigma R is the elementary symmetric function. Sigma R. Oh, just a minute. Sigma R is the elementary symmetric function in R there. The rth elementary symmetric function. Yeah, the rth elementary symmetric function in these variables. Okay. So the rank is the dimension of the maximal torus that it contains. Okay? So the rank of G, so the rank of H is the dimension of the maximal torus of H. Okay? So every Lie group has every compact Lie group has a maximal torus. And all the maximal tori are isomorphic, are conjugate, so they all have the same dimension. And that dimension is called the rank. So for example, when you, this has maximal rank because it contains n copies of U1, right? That's the maximal rank. This also has maximal rank because UK has k copies of U1. This is n minus k copies, so you have n copies of U1. And that's the maximal rank in UN. Okay? There's a theorem that if you have a closed subgroup of maximal rank, then the quotient is actually complex algebraic variety. Okay? And then if you don't have maximal rank, you can actually prove that all the topological invariants are 0. So there's nothing to compute. Okay? Yeah. So So this formula you can find in my paper that's called Computing Characteristic Numbers. Using fixed points. And it is in the, the Center for Research in Mathematics Proceedings 50, 2010. Okay. Yeah, so in this paper, I work out all kinds of formulas using the localization formula. And then okay. Yeah. Okay, and then we get identities. So for example, now if you apply to CP2, which is lines in C3, you apply that formula to CP2, and you compute, say, this term number, C1 squared. Okay. Now C1, S is the universal subbundle, so it's a dual of the hyperplane bundle. So C1S is minus the hyperplane class. And if you take its square, that means you are computing the intersection of two lines. Okay? A hyperplane in CP1 is a line, right? So you're computing what's the intersection of two lines in CP2. Yeah, two lines intersect in one point. So this integral should be 1. Okay? You can work it out geometrically. But if you use the localization formula, you get a formula like this. And that formula, in this case, will be the sum of ui squared, where I goes from 1 to 3, over the product of ui minus uj, where I is less than j. Excuse me, is it I less than j? Or, no, I think it's all I, all j, all I, yeah, j is the complement of I, so all ij not equal. Anyway, yeah, so you get some rational expression. And it's not obvious that it's equal to 1, but if you simplify it, it becomes 1. Okay? Yeah. So, so these formulas will give you all kinds of, very interesting identities like this. And then another application is to Pappus's theorem in geometry. Okay, Pappus is a Greek, so from more than 2,000 years ago. And do you know, have you ever learned about Pappus's theorem about a sphere? Have you? Yeah, what does Pappus's theorem say?
Something like a disk of when you want to compute like shape, you got to like the volume of it, you got to compute the length of the path of its center.
Oh, okay. So yeah, something like that. So you want to, Pappus's theorem says that if you slice the sphere with horizontal planes, okay, say like there, and if the distances are equal, then the surface area of the sphere that you cut out are equal. So you see this and this, okay, they have different shapes, right? Because it looks like this one, well, in terms of curves, this curve is longer than this curve. Yeah. But Pappus's theorem says that if the two vertical distances are equal, then the surface areas are equal. Okay? That is Pappus's theorem. And, of course, you can prove Pappus's theorem using calculus by computing the surface area. But you can also use, you see, equivariant cohomology because let's say this is A, this is B, okay, Z equals A, Z equals. Then you want to calculate the integral, so let omega be the volume form of the sphere. So you want to calculate the integral omega between Z equals A and Z equals B. And you can find its equivariantly closed extension and then this integral is the same as this integral. Okay? And then you can use the localization formula to calculate this integral because omega is equivariantly closed. And and you get 2 pi over b minus a as your answer. And so that proves that if the vertical distances are equal, then the surface areas are equal. Okay? Yeah. And then now, very, very quickly, just mention that you can also do symplectic geometry using equivariant cohomology. Because a symplectic manifold is a manifold that has a closed, non-degenerate 2 form on it. Okay. A closed, non-degenerate 2 form. And a group acts symplectically on M if it preserves that form. Okay? But that says that omega is an invariant form. So if G is connected, this is equivalent to the Lie derivative is 0. Okay? And then then you see the dIx of omega, it's Lx minus Ixd of omega. And that will be 0 because Lx is 0 and d of omega is 0. And so Ix omega is exact, it is closed. Okay? And if Ix omega happens to be exact, say Ix omega is df, then the action is said to be Hamiltonian. Okay? But you see, this is precisely the condition for omega to have an equivariantly closed extension. If you have this, then omega tilde is omega plus fu is equivariantly closed. Yeah. So that says that if you have a Hamiltonian action, then omega has an equivariantly closed extension. Now, all this Hamiltonian action, it is classical mechanics. Okay. So in classical mechanics, you have Newton's law and all these laws of motion. They can be translated into symplectic geometry. And then in symplectic geometry, when you study Hamiltonian actions, then it turns into equivariant cohomology. Okay? And so equivariant cohomology application to physics. And then finally, so in physics, you often have to compute integrals like this, e to the ITF tau. And you can compute them using the localization theorem if you have an action, of a torus on M, and with isolated fixed points, then you can get a formula like this. As the integral is a sum. Okay? Yeah. So these are some of the applications of equivariant cohomology. Okay? All right. So I'm going to stop here, and on Monday we'll just have 1 hour, and I will go over the proof of the equivariant Durand theorem. Okay? And then that will be the end of the course. And then Monday evening we'll have a party, at my grandfather's house, where nobody lives, so it's really good for a party. Yeah. Yeah. All right. Good. So if you can hand in your homework.